Good. Thank you very much. It's always a pleasure to be in this bookstore. You got all the nines right there, 99.9999991% the speed of light, but that's at 14 TeV, which is 14 trillion electron volts, which is a maximum energy achievable by the Large Hadron Collider. As most of you know, that's not the energy at which the protons are crashing right now as we speak. They're crashing at half the energy, 7 trillion electron volts. And the reason for that is that CERN is like a person, and it's traumatized. It's traumatized for 2 years now, since September of 2008, when everything was ready for the big moment, crashing protons at 14 TeV. Immense amount of energy, 7 times more than Fermilab, the Tevatron at Fermilab, which is just under 2 TeV. The Europeans are interesting people, as you know well. They're always champagne bottles, and it's a shame I can't show you my pictures. I have a picture actually of the champagne bottles, among other things. And every time they reach a landmark and beat Fermilab with energy or make a discovery, there are champagne bottles that pop open sort of spontaneously. So they're ready with the champagne bottles, and they went actually further than that. What they did is they invited heads of state. CERN is a European concern. It's supported mostly by Germany, France, Belgium, and all these European countries. France, Switzerland, and Germany are the biggest supporters, and then there are other countries. So heads of state of Germany, France, and Italy, and other countries were all ready to come for LHC Fest. That's in addition to all the champagne bottles. And the machine crashed. So they had to cancel the LHC Fest, and all these people went away, and it was an immense disappointment for everybody. Is this working, by the way? I don't think so. Yeah, okay. So I'm used to speaking without it. Would it work without a mic? If I talk loud? No? Okay, sorry. So what happened was a trauma. And when you go to CERN and you speak to the scientists, and I've been very fortunate to be invited there, I still don't understand why I was so lucky that every door was open to me. I've written a few books before about physics, but I had no idea that people would welcome me so warmly. So I actually went inside the machine before it was closed for the proton collisions. But I was talking about the trauma. Every scientist I met there say, well, 2008 was a big problem for us. We don't want it to happen again. What they did is like buying a new car and revving the engine as fast as it can go. And of course, you can burn an engine when it just comes out of the factory. It happened to a lot of people. So now they're running it very slowly, and they're at half speed right now. So actually the speed is 99.9. There are a few nines there, but it's close to the speed of light, and we'll get to that. So at any rate, I was able to visit the machine and go inside this big detector. There are 2 large detectors. One is called Atlas, the other one is called CMS, which stands for compact muon solenoid. Muon is a particle that comes to us from the upper atmosphere, as many of you know, and we're being bombarded by muons all the time. When you fly in an airplane, they tell you get radiation. That's mostly muons. They're like electrons, but they weigh 207 to 209 times what an electron weighs. They're very heavy kind of electrons, and muons are among the main particles produced in these collisions. I'll tell you a secret. You all know, I'm sure, that the machine is looking for the Higgs boson, the so-called God particle that gives all the particles in the Standard Model their masses. The Higgs is determined to have been created by the machine if you find 4 muons. And they come out one up, one down, one to the right, and one to the left because of conservation of momentum. So they have to cancel out because you start with 0 momentum away from the beam, and it has to add up to 0. So there are 4 of them in a cross, if you will, or something like that. And that's what they're looking for. If you see 4 muons, that's a telltale of a Higgs boson. So that's what they're looking for. And the machine was built at the cost of $10 billion. 10,000 scientists work there from around the world. Many Americans work with CMS, by the way. Atlas has scientists from other countries. And they're all, CERN is an amazing place. It's the only place that I know of where 10,000 people work in perfect harmony. Now you might be skeptical and say, how could they work in harmony? But they do so a lot more than in any other place that I've ever visited. There is competition. The two teams, CMS, Compact Muon Solenoid, and Atlas, compete with each other. One of them may discover the Higgs while the other may not. So they are fierce competitors in some sense, but they also share information and they have tea together and they go to each other's houses. So they tend to be very good friends. The one reason for that is the corporate culture that began at CERN. CERN was founded in 1954 as a reaction to the Manhattan Project in the United States. What the Europeans wanted to do is to pursue the secrets of the atom for purely peaceful purposes. And they gathered European scientists, remember this was after the war, and they wanted them to bring science back to Europe because the brain drain because of Hitler was affecting them very badly. Most scientists left their positions. All Jews had to either leave or be stuck and not come back. So many came here, others as well left Europe, and the CERN was established to lure back all these physicists and other scientists to something that would be done together, a research enterprise that will be the largest in the world. And it reached that stage now with the LHC. The LHC is the largest machine ever built. As you mentioned, 16.5 miles in circumference. It's 300 feet or 100 meters underground. And it has, Atlas is the largest scientific instrument ever built. It's 7 stories tall, and it's 7 stories high. And CMS is a little shorter. It's only 5 stories high, but it's the heaviest scientific instrument ever built. It weighs 12,500 tons, while CMS weighs only 7,000. Even that is about the weight of the Eiffel Tower. So what you have here is the greatest, the best, the most advanced of everything. The largest machine ever built, the heaviest and the largest scientific instruments in it. And in addition, the LHC is the coldest place in the universe. How can we know that? Why is it the coldest place in the universe? Well, the temperature of outer space, I know there are physicists here. What's the temperature, cosmologists? What's the temperature of outer space? Anybody know? Well, it's 2-point-something degrees Kelvin. It's above. And the reason for that is these are the embers of the Big Bang. The Big Bang was very hot, and the universe has been cooling as it's been expanding. It's been cooling very slowly, and now it's cooling very slowly, and it's at 2-point-something degrees, 2.3-something degrees Kelvin. The LHC is almost a degree lower than that. The reason for that is that the machine is run with magnets. These are very large superconducting magnets, and they're superconducting so that electricity will go through them without resistance. In order to achieve that, you have to have a very low temperature, and that's created using liquid helium. Now, the liquid helium wants to be a gas. So to make it liquid, you have to put a lot of energy into it, and once it's there, it evaporates. So you constantly force it to be cold, and that's how it's colder than outer space. In outer space, whatever wants to be a gas becomes a gas. So if you create something, putting energy into it, that's colder. You make it colder than outer space. So it's the coldest place, and the protons in it fly at that 99.9999991% the speed of light. Now it's 99996 something. So it's not quite, but it's getting, as the energy goes up, it gets faster. To give you an idea what these nines mean, a photon, a particle of light coming from these lamps, travels at the speed of light by definition. And Einstein has shown us that that's the maximum speed in the universe. That's the speed limit. You can't, now, if you talk about the expansion of space, you get to other those of you who know physics know space is expanding faster if you're on 2 different sides of our universe. 13.7 billion light years in one direction, the other side, they recede at a faster speed than the speed of light, if you can believe that. But within a given piece of space, the fastest thing that you have is a photon. It travels at the speed of light is 186,000 miles per second, roughly. Now, the protons are accelerated to a very high percentage of that speed. If a photon races one of the protons from the LHC to the nearest star is Alpha Centauri, which can be seen from the southern hemisphere. It's 4.2 light years away from us, which is quite a distance. It takes light 4.2 years to get there. But the proton from the LHC would get there a third of a second earlier. I'm sorry, I blew it. A third of a second later, after the light beam. So there's a third of a second difference between this very fast proton and a photon that travels at the maximum speed. So that's incredible. How do you do that? So let me tell you about the machine and how it works, because it is really the greatest wonder of in technology of our civilization. A physicist at MIT told me when he knew I was going there, said, when I went there, I felt like I was looking at the cathedrals of Europe, but these are the cathedrals of our time. And that's exactly how I felt when I was inside the CMS detector. You look up there and it looks like a cathedral. It's very beautiful, but it has all these electronics that are a marvel of technology as well. So the CERN has many accelerators because it's been an organization that's been around since 1954. They started with one accelerator, then there are larger ones and larger ones, always larger ones, because you always want more and more energy to learn more about the universe, to discover newer particles that haven't been known before. Now, those particles are heavy. They're small. They're all point particles, elementary particles. They're considered point particles, but they're heavier and heavier. So to get them to come out, you have to invest a lot of energy into them. Now, the protons come from a bottle of hydrogen. So even the most complex machine in history starts very simple. You have a little bottle that has hydrogen gas, simple hydrogen gas, the most common element in the universe. And electrically, they strip the electrons away, which apparently is a very simple procedure to do. And what's left are protons. If you suffer from stomach pains, stomach acid, these are protons. The protons in the HCl in your stomach, these are protons. So you get these protons from this bottle, and they go into the first accelerator called LINAC. It's a linear accelerator, and accelerates them to a certain percentage of the speed of light. Then they go into the next accelerator called the proton synchrotron booster, then the proton synchrotron itself, and then they go into a machine called the SPS. That's called the super proton synchrotron. That's a machine with a great history. In 1983, it's discovered two very heavy bosons. Bosons are particles that carry force. The photon is one of them. That's the electromagnetic. That's the particle, the boson, that carries the force of electromagnetism. Then you have two bosons. One of them was predicted to exist by Steven Weinberg, the American Nobel Prize winner. He named it the Z, or the Z as the Europeans call it. And the W had been sort of predicted earlier than that, but Weinberg's and Salam's, he's a Pakistani physicist who's no longer alive, their theory made use of these two bosons and of the Higgs mechanism. The Higgs mechanism is what brings these two particles alive. Now, these particles are heavy. 80 GeV, if you're interested in these numbers. So a TeV is 1,000 times more than a GeV. A GeV is 1 billion electron volts, and a TeV is 1 trillion, 3 orders of magnitude, 1,000 times more. So these are 80 GeV. The machine goes up to now 7 TeV. So you can do the math of how much more it is. And the other one is 91 GeV. These were discovered in the SPS, the super proton synchrotron, in 1983 by a physicist named Carlo Rubbia, and received a Nobel Prize for it. And there was another team that didn't get the Nobel Prize. And that was the last time that anybody at CERN didn't share information completely. So these bosons were discovered experimentally in the SPS, and that was a big success of CERN already in the 80s. So now the LHC, which replaces a previous accelerator which used the same tunnel called the LEP, Large Electron Positron Accelerator. A positron is the opposite of an electron, antimatter particle. When they get together, they annihilate each other, as you probably know from reading Dan Brown, at least. Right? I have to tell you about Dan Brown. So when I went to inside the CMS detector, my now friend, the guy who introduced me to the machine, said, and you probably want to know about the eye scanners. And I said, that's exactly what I wanted to ask you about. And he said, well, we didn't have them here when Dan Brown came. They put them afterwards. I'm talking, of course, I'm alluding to the movie Angels and Demons, where you see the LHC, actually, if you've seen the movie. So they came afterwards, and we don't know whether Dan Brown knew that they're going to be installed, or maybe they thought that that's a good idea after the book came out. And apparently the movie theater outside CERN, in one of the little towns where many of them live, was full the night that the movie showed. So they're all very excited about that. But the reason, he said, is not terrorism or whatever. It wasn't. The reason was in the movie and the book. The reason is, if you're in the tunnel and it closes and they're going to, I forgot to tell you that the magnets not only use a temperature that's colder than outer space, they also create the largest magnetic fields that created by humans. Well, actually, some are higher, but they're close to, they're 200,000 times the Earth's magnetic field. So my credit cards would be gone and all of yours. And so if you wonder what would happen to, so anyway, if the machine has to close, so if a person is down there, that's real trouble. I mean, you're 300 feet underground and you're alone and the machine is going to work. I wouldn't like to be there. There's a German physicist, my friend told me, who was there, and he wanted to experience firsthand 200,000 times Earth's magnetic field. And he stayed while the tunnel was closed. So he ignored the eye scanners that tell the computer, there's a person down there, don't close it. He remained there, and the machine closed, and he was right within a magnetic field, 200,000 times the Earth's magnetic field. And he survived. And he came out later, he said, well, he was very kind of terse. He said, it's okay. If you don't move, you can survive it. But apparently when you move in a magnetic field, the pressure on your head is immense. So he just didn't move at all. And that was tolerable, which was interesting. So, at any rate, there are all these things about, the greatest, the biggest, and the investment, $10 billion in an accelerator. So the protons leave the SPS, which was the last word in accelerators in 1983, and then they are fed into the Large Hadron Collider. It's 60.5 miles around, and the protons go at maximum speed. They go 11,400 times around every second. Well, you can do the math again. 26 kilometers or 16.5 miles divided into 99.9999, etc. the speed of light, and you can see how fast how many times they can do that. This is just time and distance and speed. So what are they looking for? Why? I can see the questions in your eyes, although some of you know the answers. Why invest so much money, collect 10,000 people to live there in the middle of nowhere? I have to tell you about the black hole. I'm talking fast because we wanted to make this short, and I know the best part will be your questions. So I'm rushing through so that I can get to your questions as quickly as I can. So if you have a question about the black hole, do you? Well, that was my first question. That was the beginning of the search. I wondered about the black holes. I talked to lots of physicists, about 50 of them. I spoke to 13 Nobel Prize winners in physics and lots of others who should have gotten or will get the Nobel Prizes. And I asked every one of these physicists, including experts on black holes. I sought out 2 experts on black holes. One is Leonard Susskind, whose book is here, I'm sure, The Black Hole War, who's a big expert on black holes, and the other one, Jacob Bekenstein. If you know about Hawking radiation, it's called Hawking-Bekenstein or Bekenstein-Hawking radiation. They're both of black holes. So they're both experts on black holes. Nobody would say that the chance of a black hole created by the LHC is 0. Not one person would tell me that. But they all said the chance is very, very small. But it's possible. So this was the beginning of my search. I guess I was attracted to this Have you seen the video? Maybe online. There's a video about a black hole swallowing the Earth. It's been viewed by 4 million people. Anyway, on YouTube. If you want, I have 2 videos on YouTube actually about CERN. But that was my question, and nobody would say that it was 0, but everybody said the chance is very small, and if a black hole is created, it will be very tiny, and it won't swallow the Earth. It will evaporate within a fraction of a second before it reached the detector walls. So the reason it's believed to evaporate if it's created is because of Hawking radiation, or Bekenstein-Hawking radiation. For a star that became a black hole, the time that it takes to evaporate by Hawking radiation, it shouldn't evaporate. It evaporates because of quantum phenomena around the surface, the horizon of the black hole. It takes 10 to the 70th power years, meaning 1 with 70 zeros years before it evaporates. So it's from my point of view, that's forever. But anyway, a tiny black hole created in the LHC, if it is created, is supposed to evaporate in a fraction of a second, 10 to the minus something second. So, but Bekenstein did tell me something very interesting. This was before my first trip to CERN, so I was a little worried. I'm kind of a worrier. So, I was about to go to CERN, and he said, very coolly, said, well, of course, the chance is very small, but you should know that if a black hole is the size of a molecule, it weighs as much as a small mountain. So if you're hit by a black hole, it doesn't have to evaporate, that quickly. I mean, all it has to do is hit me, and it's like being hit by a mountain. It doesn't have to swallow me. So that was a sobering thought. But the end of the story is I took my daughter there. I have only one child. She's 20-year-old. Now she's studying physics. And I took her, and we stood right above where the protons are crashing at half the energy. But still, that's still pretty good, 7 TeV. So I promised to tell you the reasons why we built this machine. It's not that we want to create black holes, although Stephen Hawking, of course, hopes for a black hole, because that would prove Hawking radiation. But the machine was built to look for, this is the main purpose of the LHC, $10 billion, 10,000 scientists, this investment, build the greatest machine ever in history, to look for what's called the Higgs boson. And not everybody is sure it exists even. So we're looking for some particle that may or may not exist. This is the particle that, according to Steven Weinberg's calculations and Abdus Salam, is needed to break a primeval symmetry that existed in the universe. So if you think of, we're really getting close to the Big Bang. That's the whole idea of the machine. You can look at it as creating particles or bringing them back to life from the early universe, or getting closer to the Big Bang. According to theory, we can't get to the Big Bang the same way as we can't reach the speed of light with a massive particle. That's impossible. You can get to 99.9 and more nines there, but you can never reach the speed of light with something that has mass. The only things that travel at the speed of light are massless things, photons. So the idea is to get to something like less than a trillionth of a second after the Big Bang. Now, if you think of the Big Bang as an immense burst of energy, that energy has no mass in it. Good question. So the question is, weren't we going to have something like that built in Texas? And what happened to it? So yes, we as Americans want to have always, if the Europeans were going to have a machine that goes to a certain number of TeV, we want to have a bigger one. And the SSC, the superconducting super collider, was supposed to be more powerful than the LHC. And every physicist in the world is upset with the Congress. Not every physicist in the world, but many, all particle physicists in the world are angry with the Congress for not continuing the funding. The tunnel had already begun to be dug. Part of it exists there in a town in Texas whose name I can't pronounce. Everything was ready, and all they needed was continuing funding, and the Congress just cut it in 1993. Why? I don't have an answer to you to that. It just wasn't in the cards. The congressman didn't want to vote for it, and that's it. Steven Weinberg, who I mentioned now the third time, went in front of Congress and tried his best to get funding for it, but another American physicist, a very, very good one called Philip Anderson, who is a condensed physics scientist went in front of Congress and said, no, it's unnecessary. It's too much money. We, condensed matter physicists, do physics without such an investment. It's not necessary. And the Europeans just grabbed the ball and ran with it. And they built a bigger machine. Now it's the biggest machine in the world. The SSC would have been the largest machine in the world. And what happened is most American scientists who are into this kind of research are involved with CERN now. Without being European, they're members in CERN through their institutions. MIT has tons of physicists who go to CERN back and forth, and many other American universities as well. The Americans are with CMS. Other countries, some of them are with Atlas. So, and CERN, if I understand correctly, their recent vote in the executive committee, they're making it more international to make it easier for Americans to be involved now that 17 years now we lost it, the SSC. I hope I answer your question. Good.
Okay, here. Is there any kind of theoretical limit or sort of practical plateau on the amount of energy that you can get with one of these things with the current state of technology?
Yes, good question. Well, you can't get to the speed of light. It's just impossible, but you can get closer and closer and closer to it. There's something called the Lorentz factor from special relativity, and it climbs up. So to raise something to a certain speed takes so much energy. So I kind of didn't give you the numbers, but the earlier accelerators get in terms of numbers, 99. When the protons go into the LHC, they're already at 99, above 99% of the speed of light. It's the last 1% that takes the highest. So it's like that. It's exponential. It looks like an exponential. So it goes faster. Well, it comes from Lorentz factor. You can see. It goes very steeply, and if you put more and more energy, you can get them faster. So CERN right now uses the amount of electricity that lights and gives power to the city of Geneva. So it's outside Geneva. Geneva is here. And the airport is right here, and the center of CERN here is here, a place called Meran, just a suburb of Geneva. When the city of Geneva it gets its electricity from a French company called EDF, and when the CERN is running, they supply twice the energy. Half goes here, which is the full amount they always use, and the same amount goes to CERN. So, if you want to get the particles closer to the speed of light, you need maybe twice the energy. So you invest in this electricity. The LHC is running below its energy because they're worried. I didn't tell you what happened in 2008. What happened was a welding just broke, burnt, melted, and these magnets started burning. There was fire inside the tunnel. 53 magnets failed. They quenched, that's the word. They lost their superconductivity, and heat started building up. So if you go, the LHC can't go above 14 TeV. So I mean, it will burn. It's like trying to run your engine at a certain speed. But they're building a new accelerator already. They're always a step ahead. And I happened, because all these doors were so magically open to me, I got to see the next accelerator. There's a prototype for it, which is about the size of this room. And there are radiation signs everywhere, and it's not because it's not a Dan Brown novel. There are radiation signs everywhere because they use parts from old accelerators. So it was not very pleasant to stand there. All the parts are radioactive, because many of them, because they came from older accelerators, and they're made. Some parts can work even though it's a smaller scale. So it's a whole accelerator, and I keep going like that because it's a straight line accelerator. Accelerators are built in two designs. There's a straight line and there's a circular one. The straight line is easier. You don't need as much energy because you don't need those magnets. And magnets, most of them are there. Some of the magnets focus the beam. Other magnets do other things. And the protons are accelerated with electric fields, not with magnetic ones. The magnets are there to bend, to constantly bend them. You see, particles want to go in straight lines. That's physics. I mean, the inertia continues. The momentum stays where it wants to go. It goes where in a straight line. For it to bend around the circle, you have to force it to bend. That's where the energy goes. All that electricity supplied by EDF, most of it is used to bend them. So there are advantages and disadvantages. The linear accelerator, such as at Stanford called SLAC, this Stanford Linear Accelerator Center, is a straight line accelerator. The particle starts here and ends there. There's no more, no other place to go. But in a circle, you go round and around and around until people decide you'll crash now. And so otherwise it has to crash when it reaches the end. But the next accelerator at CERN is going to be 40 kilometers long, which is not that much longer, but a straight line. I'm not sure why they're looking at that, other than they think they can reach higher energy still, or about the same, but with less cost. So, but the real answer to your question is there is a limit. To prove string theory, for example, you need a huge amount of energy that nobody hopes to get in our lifetime. Maybe it's an amount of energy that will start affecting the planet. You know, if you're going to use so much more than the electricity we need, and think of carbon emissions and so on, you can see there is a limit to energy. So I hope I answered your question. Good. There's a small, to repeat the question, if they don't get the Higgs, does that mean we need more energy? There is a speed of light going with the energy, right? So the speed of light, or the energy to get it too close to the speed of light. And in fact, it's all about energy. They go to a high speed so that when they crash, they have a lot of energy. Because by Einstein's equation, E equals mc squared. So you can say E energy is the same as mass. So the conversion factor is c squared. So what happens with the protons, they crash at very high speed. The speed itself is not important. It's just an after effect. They have energy because of their speed. That's the kinetic energy. When they crash, their energy turns, they turn themselves into sheer energy. That energy turns into massive particles. That's how the Higgs is supposed to appear, out of sheer energy because of the crashing of the protons. And that's because mass is the same as energy, it will occur. Now, why would it occur? Because in quantum mechanics, if something can occur, it will. So it's a rare event, and that's why they need to run it for a long time. But it didn't answer your question. Your question is, what happens if the Higgs is not found? Does that mean we need more energy? The short answer is most probably not, but some physicists think that the Higgs may... I want to draw sort of a picture. So there are hints of a Higgs already. When I went to CERN, there's a big display there that shows the biggest hint of a Higgs, 4 muons. But there's only one picture. Somebody saw 4 muons in a previous accelerator called the LEP, which I mentioned a little earlier. Same tunnel, the same length, but lighter particles, electrons and their opposites, antimatter particle called positrons. They crash together and they annihilate each other. So it's a cleaner kind of collision because particles and antiparticles annihilate each other. Here, it's a crash. It's a dirty crash. Particles go here, there, and some of them turn into energy. Now, what happens is, because of LEP, we have some ideas about where the Higgs mass is, and also because of Fermilab. Fermilab, the tevatron at Fermilab, got some bounds on the Higgs mass. And the bound right now is 114 GeV, which is, well, 114 over 80 times larger, heavier than the W boson. The Z is 91, so they're all around the same. The two that were discovered in 1983, the W weighs 80 GeV, the Z weighs 91, and the Higgs is believed to weigh 114 GeV or more. So the present assumption is that it exists somewhere between a mass of 114 to 180 or so. Then there's an excluded region because of experiments that have been done at other places, LEP and tevatron. And they leave out a region where the Higgs cannot exist. Then there's another region somewhere. There may be a heavy Higgs. I went to lots of conferences on the latest in particle physics. There's an assumption of a heavy Higgs, a light Higgs, and then between Higgs, a supersymmetry Higgs, meaning supersymmetry, the other theory that I mentioned, has its own Higgs. And there are alternatives to the Higgs altogether. The most likely possibility for reality is a light Higgs. That's what most particle physicists believe, and is a light Higgs, which means 114 to 180 GeV. That's well below the power of the LHC. I would say that the vast majority of particle physicists in the world think that the LHC is well capable of finding the Higgs. But if it's really heavy, well, maybe the next accelerator is needed for that.
I was just curious about the two accelerators you mentioned, the one at the CERN and the accelerator in Texas. What is the limit? Where does the size limit come from? I mean, is this just a matter of having the materials and having the materials and the energy to run particles that on a 16? Sorry, I forget the distance you were talking about. But why couldn't you build one double the size of CERN?
Yeah, let me try and answer that. So here's how it works. The problem with CERN is really the magnets. That's the weak point there. It's the magnets. Because getting those particles accelerated is easy. You have a wave that just gives them a kick. Every time they pass by, they get a kick. But as I said, the problem is they want to go straight. Particles want to go straight, so you have to constantly bend them. Now, let me try and give you an example. Suppose that you're doing luge or something like that, and you go, no, the space is fine. The problem is the magnet's electromagnetic field is not strong enough to keep it if it's going faster. It has more. The faster it goes, the more its mass goes up. Effectively, its mass goes to infinity when a particle that has mass, if it tries to go at the speed of light, its mass is infinite. The best example is to accelerate a car is easy. To accelerate a truck is harder. To accelerate a ship, I grew up on a ship, passenger ship in the Mediterranean. My dad, I wrote about it in a book called The Riddle of the Compass. My dad had me steer his ship in the Mediterranean when I was 10 years old. And my trauma is I wake up at night sometimes thinking, oh, the ship is turning and I can't turn it back. Same thing. You've got this accelerating a ship or turning a ship takes a lot of something. But I didn't answer your question, so let me try and answer it this way. Imagine you have a force that's exerted. I'm a proton. I'm going around the 16. The walls of the tunnel don't matter. It's the electromagnetic field that holds me in place, right? The field pushes against me. It needs energy. 11,700 amps go into these. If you try to raise it to 20,000 amps, you need to have thicker wires in there to get all that electricity in there in time, right? To do that is harder. You have to build a bigger magnet, and the magnets have a certain limit. So you have to, well, you can build larger ones. Also, the tunnel has to be with a higher circumference for that to happen, because you really want somewhere in between a straight line. Look, if you can't accelerate them here and expect them to go very fast, right? Because the turning radius is too high. So at 16.5 miles, they are almost at the straight line here, and the magnets keep bending them all the time, and it works. If you want to raise them to a higher speed, they become like a truck and later like a ship. They have more inertia. You need to kick them further in. So I hope that answered it. Yeah, that's a good point. You've got people building this machine. It took 20 years, $10 billion, all these scientists there. And suppose it started with finding the Higgs. That was the first purpose. So they came up with all the other purposes too, as backup. What happens if there is no Higgs? There's something else. Well, we need to find something to justify the investment. And that's a very, it sounds like a joke, but it really is a very real concern, because physicists who work in research institutions, not at universities where they teach and write papers, when they work in a research institution in a lab like CERN, they are fully supported by their governments. Their governments give money to CERN to support them. Now, the biggest fear of people at CERN, other than another breakdown of the machine, is the Higgs won't be found. What happens then? Well, hopefully they'll find dark matter. Another experiment at CERN, not those two that I keep mentioning, a third one called LHCb, is looking for matter, antimatter, and asymmetry. Why is matter different from antimatter? If they find something there, that would be a big enough. Look, the SPS itself justified itself by finding these two bosons, the Z and the W. So if CERN finds dark matter candidates that are then proven to be, yes, this is dark matter, or it finds a hidden dimension of space which supports string theory, not directly. To support string theory directly, you need a huge amount of energy. But to find an additional dimension of space-time, which, our universe may have more dimensions than the 4 that we know of, 3 of space and 1 of time. If they find a hidden dimension, that would justify the investment. So the answer is yes, the Higgs may not exist, but hopefully one of the 4 or 5 or 6 aims, and they keep going down in priority, will be discovered to justify the investment. And there's something else in addition to all of these. When I spoke to the heads of the experiments at CERN, the 2 heads of the 2 teams, CMS and Atlas, one of them said to me, what we're really hoping for the most is something unexpected, something totally unexpected. So you have all these stated aims which come out of theory, and then there's something that's totally unexpected. And you say, wow, well, this already happened. The Higgs hasn't been discovered yet. The supersymmetry, or which goes together with dark matter, hasn't been discovered yet. A hidden dimension of space. Now you might say, how did they discover a hidden dimension of space? This is really interesting. They're jets. The jets are quarks that go together. So they go in this direction and that direction, and there's something goes here. I mentioned conservation of momentum. So it's sort of the masses in the direction have to balance out to give you 0. And if they don't, and there's a lot of missing energy, imagine particles in the jet go out here, and something is missing here to balance it all. That's a hidden dimension of space. It could be that all that energy disappeared somewhere. It went to another dimension. So that's another possibility. Because you start with 0 momentum in this direction, so it has to add to 0. Why is 0 in this direction? Because everything moves this way, right? So when you have particles that are created and they move in this dimension, they have to balance out. Something goes here, something has to go there. Makes sense, right? Now, this angle and that angle are correlated, and they have no idea why. That's the big unexpected finding. If you go to online to news about physics, you'll find it's happened. It was released to the media on the 25th of September. So it's very recent. They're still scratching their heads at CERN, trying to understand what it is. And there are many theories about it. What came to my mind first is entanglement. They're entangled. But that's not one of the theories that are being pursued. It's a possibility, but it's not something that's pursued. Well, if you know, I wrote a book on entanglement. That's why it came to my mind. So 2 more questions, right? Yeah.
How's proton collision going to help in discovering dark matter?
Well, the protons are crashed together to release energy. And so what you have is E is equal to mc squared. So when you have one particle here and one here, and they crash together, they sacrifice their They sacrifice their mass. Maybe hidden dimensions of space will indicate that string theory is right, and string theory is the theory that has the best chances of putting together general relativity with quantum mechanics. But leaving that out, you have special relativity, which is E equals mc squared in this aspect of it, together with. So you have all this energy. The energy turns into mass because of E equals mc squared. So you've got mass with kinetic energy turning into shear energy, energy turning back into mass because it can. That's why it does that. That's how all these particles are being discovered. The tau lepton was discovered that day. That's why physicists have a trust in this idea, because they've been doing it for 60, 70 years. I forgot my microphone. And the other theories use differential geometry. So you're really looking at manifolds and trying to connect them. So those Lie groups actually exist there too. So it's a very beautiful mathematical theory that links together the continuous world of manifolds of differential geometry. You have the idea of the calculus, continuity, and you have the more discrete things that are groups. It's a beautiful theory, but it requires a lot of energy, and nobody knows if it's true or not. Mathematicians think that it's true. Physicists, some of them, the older physicists are more skeptical about it. The younger ones, Harvard, for example, has lots of string theories. Lisa Randall and others. So and Vafa, whom I mentioned, Kumar and Vafa. So it's a modern theory. It's a new theory. It hasn't produced much by way of answer. It solved theoretically the problem of the entropy of a black hole, and that's our biggest theoretical advance. When I interviewed Roger Penrose, he said, they only had this idea about black holes, that's all. So it depends, is the glass half empty or half full? Black hole entropy is a lot if you believe it's a lot, or it's not much if you want to believe that string theory is not good. So I hope that answered your question. One more, this is it? Okay. Well, thank you very much.